Hello, my name is Clemens. I work for Microsoft and I'm the architect for the messaging services in Azure. And today we will do a session that is brand new. The material has never been shown before. And what we have not done yet before is show you Service Bus, kind of the internals at that level of detail that I'm going to talk about today. So the second half of this talk is literally how does the cluster work? How does everything that sits behind the namespace name, how does that actually function, right? How is Service Bus built, and how is it different from a broker you would go and install on a VM? And what you'll find is that between the broker that you would install on a VM and that whether the hosting model really hasn't changed in 25 years, and what we do, there is literally 25 years of technology difference there. So I'm going to go and try to explain most of that to you. What I will also do, and that's in the first half of this session, is I will talk about the patterns and features, and I will enumerate some features that you may not be aware of in Service Bus. And I will go and give you some kind of conceptual ammunition about Service Bus. I will do no demos, because demos are for Service Bus for messaging are like, how do you demo TCP/IP? Yes, I can send a message. Yes, I can receive a message. That's all exciting. Here's a console app. There's a console app. Thank you very much. So you can go and have that demo in your head. So instead, I will talk about what you can do with that sending and receiving, and what are the features you can go and use in the product. And that conceptual knowledge will help you no matter which of the SDKs, which I will also enumerate, you use. Right? So generally, we are there to send messages from A to B through a queue or through a topic. And I will go and explain then further features, and then we're going to go and do the deep dive. What is Service Bus? It's a platform as a service queuing and PubSub message broker. Very similar in nature to many other products of the same category. It's a very mature category in software. There's IBM MQ, which has had 1,000 names, WebSphere MQ, MQ series, and now IBM MQ, that has existed since really the mid-60s and was kind of the first product of that category that was developed for the Apollo program on the IBM 370. So that was kind of the first queuing broker. And kind of since then, there have been TIBCO EMS, there have been Red Hat AMQ, there's several Apache projects, Cupid, Rocket MQ, Active MQ, there's Rabbit MQ, there's all of these message brokers, and they are all in the same category of queue-oriented brokers. It's a fully managed service, which means you don't need to worry about anything. You just go and you go to the Azure portal or you use our CLI tools and you create a namespace, and that's the broker for you. I will show you what that looks like, or what the broker is. But beyond this, you don't worry about disks, you don't worry about CPUs, you don't worry about keeping that thing up. We do all this for you in a fully automated way. And we're standards compliant with JMS 2. Meaning that most Java applications in particular are binding to queues using the JMS2 API. It's in the Java world the most successful abstraction API for enterprise infrastructure, far more successful even than JDBC, because it really works that if you have a JMS application today and that JMS application runs against IBM MQ, you can move that to Service Bus basically unchanged. If you are just using the JMS2 features, which are plentiful, then it can be done. And we also support the MQP standard, which is the Advanced Message Queuing Protocol, has been developed by numerous companies, many of them customer companies from the financial industry, and we're also fully compliant with that. I'm also going to call out the stacks that you can go and use to talk about this. And then we have numerous Azure SDKs that work with Service Bus. Service Bus is a Ring 0 service, which means it exists everywhere in Azure. When there's a new data center, new region existing in Azure, it automatically comes with Service Bus to boot, because there are a ton of Azure services which themselves depend on Service Bus. So Service Bus is a core dependency in Azure. New region in Azure announced When it's opening for customer business, even before GA, it has Service Bus inside of it. And we believe that we have industry-leading reliability and availability. At the end, I'm going to also talk about that. Before we get into technical details, let me talk about pricing quickly. Service Bus Standard has a consumption-oriented pricing. So you pay a base fee of $9.72, and then you can have up to 50 namespaces. That's actually untrue now. Now it's 1,000 namespaces. Someone corrected me and I didn't correct the slide. So you pay one base fee per subscription, and then you can just go and make namespaces as you like. So you pay this, the monthly, it's basically a monthly entry fee, but it's not per broker or per namespace, but it's really for everything that you do. And then you have 13 million operations per month included. And an operation means you send a message or receive a message. And they are free. And then from there, 13 to 100 million operations per month, you pay 80 cents per million. And then if you do more, then you have from 2.5 billion operations per month, you pay 20 cents per million operations. And then there's another Service Bus basic version, which has only queues, and that's purely just consumption-based, 5 cents per million operations. That is super cheap. It is not expensive at all, and that's something that you can do a lot of work with already. And that is using a shared resources model. What that means is I'm also going to explain. And then we have Service Bus Premium, which has a capacity pricing-based model. And that's running at 90 cents per hour, coming out to $670 per month per messaging unit. I'm going to explain what the messaging unit is. But then there are no further per operation charges. The way how this works out is that if you have sustained traffic on a queue, or on the namespace really, of about 600 messages per second, 24 hours a day, and then by average, you may have more sometimes, less sometimes. But if you have a sustained rate of 600 messages per second, that's where the cutover point is between those two. So that's when Standard, even though it looks very cheap, suddenly becomes more expensive than Premium, and that is about at that rate. And then you're getting into that far more capable tier. The Service Bus Premium has an isolated resources model, meaning that we guarantee you the exclusive ownership of cores and memory. And that means we can also do more features, we can do more for you in that reserved capacity than we can do in the shared resources model. Again, that's something I'm going to explain. And only Service Bus Premium, because of that isolation, supports the full JMS2 feature set. What you will find out is that those two services here are not just knobs that we turn on or off. This is not arbitrary. There are actually different architectures underneath. There are two completely distinct products which have a large overlap in their API. Okay, so and another advertising. If you use JMS2 today and you run a broker inside of your own data center, you can replace it. You can create a VPN bridge into Azure. You can create an express route bridge into Azure. And the broker that we have will have more uptime, be more reliable than the thing that you run on premises. And that's what we see customers doing. Customers are effectively abandoning their $500,000 per year clusters that they run on premises for MQ and use Service Bus from the cloud for their on-premises workloads. Because it's a viable replacement, and it is as full-featured for a JMS customer as their on-premises broker is. And really, for many scenarios, we are not further away in terms of routing milliseconds than that on-premises broker is, because there's usually because of the cost, this one central massive broker that sits somewhere in the middle and costs enormous amounts of money. And if you think about what our pricing is, that is far, far cheaper. There's no extra licensing costs, nothing. You only pay the pricing I just told you. Okay, enough advertising. What is a namespace? A namespace in Service Bus is a virtual broker. You create a namespace using the portal or using the CLI. What are you getting? You're getting a allocation in our system where we will take your namespace request and we'll allocate that to a cluster. We run in each data center at least one, but in many data centers we run dozens of clusters. And those clusters have well-known capacity for Service Bus namespaces. And then we will go and place you inside of them. So if you go in and say, create a new namespace, that's what's happening. We're placing you kind of into that capacity. As we're doing this, we're creating a DNS entry for you that is then aliased to your namespace. So the DNS name is a fixed name for the host for that deployment effectively. That it also has a reverse DNS resolution. And then we CNAME your namespace name onto that particular DNS name. In networking, which I'm going to explain in far more detail later, we give you a public IP address now. And then we also give you the ability to go and firewall that off. And also we give you the ability to go attach that namespace to one or multiple VNets and kind of hide the traffic from the internet. And we allow you to also turn that public IP address off if you want to. So for all intents and purposes, you're getting something that is like a broker that you create yourself, but instead of attaching a VM to the network, first of all, we do all the work for you. And second, you are connecting to a cluster, effectively a slice in a cluster, and that is your namespace. But inside of your namespace, you have now entities that you create, queues or topics. And those queues on those topics are either flat at the root of the namespace, orders, invoices, deliveries, or production. But you can also create hierarchies. So you can create a hierarchical namespace that has topics and queues at the leaves, and with that, you can create a very organized topology. And if you are familiar with how, for instance, MQTT does that, MQTT brokers do that, you can do effectively the same thing here in Service Bus. You can go and organize your namespace by categories, and then, of course, you can also go and create security policies along that path. Okay. Now let's talk about queues and the capabilities of them. When a producer writes to a queue, it sends via a networking protocol. And it does that using AMQP typically. That's the standard protocol that we use, but you can also do that over HTTP. What happens when the message gets there? It goes and adds a sequence number and a server timestamp. Can you see my you can't see that, okay. So I will, let's see whether I can do that. Okay, yes. So it adds a sequence number and the server timestamp and then writes it to the log. So whenever you write a message to Service Bus and we report it as accepted, that message has been triple replicated on disk. Nothing stays in memory. It's been triple replicated on disk, and if at that point the entire broker would crash, your message would be safe. We don't make any compromises at that front. And so sequencing means that every message that we get, that's a sequence number on the message, gets a monotonically increasing and in a unpartitioned queue gapless number that it's labeled with. And that's really determining the sequence, because we can get so many messages at the same time that the timestamps may be ambiguous. The sequence number is not. The sequence number is then assigned by a single entity inside of that broker. Timestamping is something you can do that you can use effectively as the server time for your applications, because that's a trustworthy time that we're putting onto the message. The log is ordered by the sequence number and by order of arrival. And the next message that's being delivered to a consumer is always the one that is the oldest that is available. Each message, and that is different in Service Bus from, and in a queue broker from, say, Kafka or Event Hubs, is that the broker is actually keeping track of the life cycle of every single message. Messages are enqueued, and then they're pending, because you may have a scheduled message, and the scheduled message is being, next slide, that is being held until we make it activated. Once a message is active, then it's being available for retrieval. those messages that are available for retrieval become eligible for the consumers to go and pick up. Once a message has been transferred or has been selected for transfer to that consumer, the message is being labeled as acquired. And if the message is in the state of acquired, it's exclusively assigned to that one consumer and cannot be taken by anybody else. So acquired messages are locked exclusively to the acquirer until they are settled. What that means is that the bookkeeping for who owns a message at any given point in time is done by the broker. And the tie breaking is done by the broker. And that is why this is great for job processing. The consumers, 1, 2, 3, many, up to 5,000 can be concurrently hanging on the queue. They go and take a message and do work, trusting that nobody else will do that exact same work in competition. And they can trust in that because the broker gives them that work exclusively. That is even more important for a queue than order, right? The computer science data structure queue, right? Order is the most important thing. Here, exclusivity is the most important thing. Really having a party that has exclusive ownership of that message. That is a feature that only queue brokers have. That is something that, for instance, an event broker like Kafka does not have. Okay. So the states are accepted. That's what the consumer can say. That's complete in our API, saying, I have the message, thank you very much, I took it, and now I'm done with it. Or it's released, sorry, I couldn't do anything with it, or that's also happening implicitly when the operation expires, when the lock expires, so to speak, the acquisition state. Then the message will be redelivered. As the message gets redelivered, the redelivery count is being incremented as part of the state. And if the redelivery count exceeds a certain threshold, the max delivery count, then that message is being moved into the dead letter queue. Also something we're going to get to. The max message size in Service Bus in standard is up to 1 megabyte. In premium is up to 100 megabyte. You can set messages up to 100 megabytes through the system. The way how we realize this is you put a quota onto the queue yourself. The default is 1 megabyte, but you can up that up to 100 megabyte yourself. And the reason why we put a quota there is that we don't want the messages to kind of explode in memory on your end without any warning. That's why we put that limit in there. The max queue set is up to 80 gigabytes. So if you have existing applications that transfer large documents through a queue, those will work. Okay. So that's the basic functionality of a queue. It's an exclusive assignment of jobs through a sequential log. That can then also obviously buffer those messages. Okay. Every queue and every topic subscription has its own dead letter queue subqueue. It's at myqueue/$dead letter queue. It has an address and it's usable and it's addressable like any normal queue. It's just that you can't fill it directly. But the way how you're filling it is by rejecting messages, calling the dead letter API in our SDK. What that is for is that all the messages which could not be delivered for any reason, which were faulty, have a safe place to go. And that's a transactional model that we employ here, meaning that if you're rejecting a message, you're saying from your application, hey, I've seen this message, I've looked at it, but I can't process it. It's malformed, data is bad, any reason. Then you can dead letter it, and then later someone can look at it, look at this queue, and then can go and do something about it, even edit the message, and then resubmit that message into the regular queue. And in a coming release of our Service Bus Explorer tool inside of the portal, we will actually make that editing possible in the portal itself. The reason why a message got dead lettered is always annotated inside of the queue. And then we have some further features. We have scheduling. That's another state. A scheduled message has a timestamp associated with it from which the message shall be activated, which means you can go and send messages into the queue and say, do not deliver this message before, whatever, tomorrow at 3, any point in time. So that's a scheduler. And then you can also cancel those scheduled messages before they are being activated. So if you need to have a scheduling mechanism in your workflow, then you can use scheduled messages to go and make that work. Another feature that's similar to this is deferral. With deferral, and that's also a gesture on our APIs, you can go and take a message that you've received, you're deciding that you cannot operate on it yet, and you can go and put it on the side, but keep it safe in the broker. That is typically done when you have a workflow, a state workflow, that is operating on multiple inputs from multiple sides, and the messages are effectively arriving in the false order for you to process them. Then you can go and take the message that comes too early and can go and put it on the side, and then take it back when and then process it when you have the sufficient state in your application. That's something, so state workflows use that. It's a rarely used feature, but it's something that's useful for if you are building workflow engines. For the case that you have queues that are super quiet, meaning there is only traffic, every once in a while, a message every hour or so. Those queues exist, right? We're often talking about queues that can do 5,000 messages a second, but there are very many queues for various purposes where you need to have reliable processing, but for instance, they're carrying an alarm. You want to make sure that that alarm gets handled, but the alarm is rare, and so you don't want to have resources sitting there all the time pulling on that alarm queue. So what we do is we have a feature that we expose through Event Grid, where you can go and use Event Grid to subscribe to the Microsoft Service Bus active messages available with no listeners, or active messages available periodic notifications, one of those two events. And what that one means here specifically is that if there is a queue in which a message arrives and nobody's listening on it, we will go and raise that event into Event Grid. You can now go and subscribe with a processing function, in Azure Functions, for instance, some webhook, to that event, and then wake up a function, and that function will now go to the queue, grab the message, do the processing, and then can go to sleep again. That saves cost, because you don't really need to go and run a process all the time, but you only run that only run that function. Sessions is a feature in Service Bus that gives you, in a single queue, endless number of subqueues. So you have one name, one queue that you send to, but then you also set the session ID, and the session ID labels a sequence of messages that are related to each other. Those sessions are unbounded. We don't prescribe how long they need to be. But you simply send messages. You have to go and enable that feature. You send messages into that queue, and now you have the ability to go and acquire effectively locks. The consumer acquires a lock on that entire session, on all the messages that have the same session ID. So that's what you call, that's not a receive operation, it's an accept message session operation, as we call it in our APIs, right? And once you do this, you get a lock on all the messages that are labeled with that session ID. And if you process them in order, right, you get absolute guarantees that everything that's been labeled with that same session ID is being delivered to you in order. The interesting part here is that those sessions are completely independent of each other. There's no head of line blocking, so it's no longer a queue in the sense of the absolute order is being preserved, but only the order inside the sessions is being preserved. We built this feature specifically for the workflow features inside of Office 365 SharePoint, where they have millions and millions of concurrent workflows that are going on, and of course, they can't build a queue for every single one of them. So instead, they're using the session feature of Service Bus to go and do that sort of multiplexing to the consumers, which will then go and acquire a session, see whether there's anything there for that particular context, and then read it. Now, of course, you want to go and also scale the session processing, and you want to enable the consumer here to go to sleep or fail, right, and then be resurrected somewhere else. For that, we have a feature called Session State. which means that with every session, you can store one message worth of data, any arbitrary byte data, and you can go and store that transactionally. Meaning you can go and receive messages, you can basically do stateful processing here, and you can note the progress of that state. You can note the progress of that processing against that state in that state. And you can then store that inside of the broker. And of course, if you acquire the session now on a different machine in a different consumer, you can first acquire the state and go look at the state and say, okay, so this is where I'm at. And then get the next message and process it. Again, something that has been built for workflows, but is also very useful in very many advanced scenarios. Transactions. Service bus transactions are the closest thing you can have in the cloud to a two-phase commit transaction system, right? There are transactions that are local inside, for instance, SQL or Cosmos DB and those databases. But Service Bus also gives the ability to go and get data from one place and send data to a different place and have the receiving, the settlement, really, of the receiving and the sending to one or multiple locations happening inside of an atomic transaction. You can't have that really with communication anywhere else in the cloud. So they are really a reliability anchor for performing high-value work in the cloud. You take a message, and then the transactions, when you start them, they form around a lead queue. So you say start transaction, for instance, in JMS. You start a transaction, and then you start receiving messages, and you receive them from a main queue. And then you can go and do work and then send messages to other outbound queues. The sending and the settlement of the incoming message, the completion, accepting, right? Those operations are atomic, which means if you commit the transaction, only then do the sends happen and does the settlement happen, all in one go. Which means that if the work fails, you will go and get the message again, it will do the reprocessing, but you will never leak the intermediary results. This is then usually paired with an inner transaction that you do against the database, where you're logging effectively the input message, the causality ID, whatever the message ID or the workflow, so that you can create, you say, I did this work because of this message. That's your inner transaction, meaning your inner transaction might succeed, and now your outer transaction, the sending, receiving, or something else fails, or there's a crash, power outage in the middle between those two. If that happens, then you will see that message again. You will go against your database. You see, oh, I already have handled this particular message, and then your operation will be idempotent. And that, in conjunction, gives you effectively the same assurances that you get with 2PC, with leakage of the information towards other systems being prevented by you not sending those messages out. That is the closest you can get in the cloud to the classic 2PC model, and it's the most robust processing model you can get in the cloud overall. So far we talked only about Service Bus queues. Service Bus topics are the same on the receiving end, on the subscriber end. A topic is a name that you can go and send to. And on a topic, you can create subscriptions, and those subscriptions have each a queue associated with them. From the receive end, the queues function exactly the same, and all the features that I explained to you so far are identical. But they give you the ability to go and send a message to either exclusively one of these subscriptions, if you're crafting the filter conditions such that the message only lands in one place, or it can be copied to every of those subscriptions. One topic can have up to 1,000 of these subscriptions, and every subscription can have up to 2,000 rules. What a rule is a SQL expression, or it's a simple correlation filter, which is effectively name of a property and a comparison value. These filters, the if conditions, if this being selected, can be matched with actions, and those actions can edit properties, including system properties, on the message. So it can set, for instance, a session ID, it can go and overwrite the TTL, it can do everything with that message, it can edit the message in that action. So we also have many workflow scenarios here where messages are being sent to a topic, and now that topic can actually go and have a session-full subscription, and that session-full subscription can then split itself up into 1,000 sub-queues, as you saw that before. So that's something that can be done with this. But this is usually done for effectively triaging messages, for copying messages, effective event distribution, if you will, and also for routing. A further feature that I actually don't even have on the slides is the output of a topic and the output of a queue can auto-forward to another topic without you being able to receive from it, which means that I said there's a restriction of 1,000 subscriptions. If you want to have more subscriptions, if you want to build a bigger tree, you can go and create a first level of subscriptions, which then forward into a further layer of topics, and then you can create a fan-out tree, which is then 1,000 by 1,000 at a maximum. There are some quotas you will hit there on the way out, a capacity limit, but theoretically you can go and do this. Okay, so those were not all the features, but many of the features that we have, kind of in the base topology, the things that Service Bus can do, that queues and topics can do. The way how you talk to Service Bus is through various SDKs. One is JMS, and that only exists for Java, but it's an industry standard and everybody is doing this. We've done a ton of work in the last 3 years together with Red Hat in the AMQP standardization committee, as well as in the Apache Cupid JMS project, to harmonize effectively the underbelly of the JMS driver. The Apache Cupid JMS driver is a thing we wrap. We have a different factory on top of it, which deals with authorization, token acquisition, etc. But otherwise, it's the same provider that also works against ActiveMQ and it also works against Apache Cupid. So we have standardized the wire protocol and have created extensions on the wire protocol in a standardized way so that we can share one provider with the other with these open source projects, which even broadens interoperability. So, and then we have this JMS model up on top, but what that brings us for the future is, because some of you might be .NET developers, is that we now have a foundation to make all of those capabilities available also to .NET and also in a compatible way. So that's something that we're currently noodling on how we're going to go and do this. Through Java, you get queues, topics, you get message selectors like the filters that I just talked about for the Service Bus topics, various subscriptions models. The subscription model that you usually have on Service Bus in the APIs is a shared durable subscription. And then there's these other models which are specific to the JMS model. Queue browsing, you can also peek on Service Bus queues and Service Bus topics. And then a feature which is currently still exclusive to JMS, and you could go and program against that with a pure AMQP stack, is there are queue message selectors now. So you can go and receive on a queue also giving a condition. So you can go and create a message selector against properties in the message and then only pull from that queue also without head of line blocking. You get effectively a similar effect to what we do with sessions, but you're going to get that with an arbitrary message selector. Not quite as fast as sessions, but similar. And then you can also create temporary queues and temporary topics, and you can also create regular queues and topics. You can create those purely just using the JMS client. Implies that you can now create topics and queues, and you can create these temporary topics and queues just through AMQP. Again, that's something that we haven't exposed yet in our other clients, but that's something that will come maybe towards the end of the year. We'll see how that goes. But the capabilities are there in the broker, and theoretically you can also do that with an AMQP client already. And then I said JMS transactions are supported. What is not supported is XA, distributed transactions, and that is simply because XA distributed transactions do not work in the cloud, period. And the simplest argument for why they don't work in the cloud is there cannot be a perfect coordinator. So there is no perfect transaction coordinator, and if there is no perfect transaction coordinator, then you can't have XA transactions. That's as easy as it is. You don't even have to talk about service bus or databases. The XA, the two-phase commit transaction model is dead in the cloud because it's impossible to make something that's perfect. And that's the assumption that that model has. If everything dies together on a single machine, XA works. The illusion is okay. Right? If the transaction manager and the database and the queue all die together of a power failure, all fine. Right? In the cloud, they definitely don't. And there, everything needs to be perfect, and that perfection cannot be achieved. So we support what we can, and JMS transactions is something we can support with confidence. Otherwise, we have support for .NET, Java, Spring Boot as part of the Java effort, Python, JavaScript, and Go. Those are official SDKs you can use. And they all have full product support. And all of those SDKs have been built with the idiosyncratic specificities of those languages in mind. So they are not just, we started with .NET and now we make everything look like .NET, but like a Python developer will find themselves being at home in that SDK. They all support the Azure Active Directory authorization model inherently, and they all use, except for Python, I think, a native implementation of AMQP. So there's a native AMQP implementation of Go, there's a native AMQP implementation of JavaScript, there's a native AMQP implementation of Java, native AMQP implementation of .NET that we're leveraging here. You can interact with Service Bus using generic AMQP clients if you want to. And we are doing that ourselves because our SDKs all foot on these clients. Right? We're just making the experience nicer, but you can go and rip that off completely, and you could go and interact with Service Bus also with those clients, and with that built an alternate programming model if you wanted to. But that also means that you can use any of those libraries, and then you can go and target multiple brokers that are all speaking AMQP, including RabbitMQ when you install the AMQP1 plugin. Right? RabbitMQ speaks an older version of AMQP that we call the Rabbit protocol. But if you install the AMQP plugin into Rabbit, then you can go and you can target Rabbit, AMQP, ActiveMQ, and Cupid, and Service Bus, and numerous other brokers all using the same client, using a unified approach. Similar to JMS, a little less powerful, a little less work, but across all those languages. Including, for instance, something like Azure Micro AMQP C, which is written in C99 and super compact and also works on microcontrollers. Or there's Go AMQP, there's RIA. These are not all things that we built, right? These are many things that were built in the community. Specifically, the Apache projects have been built mostly under the leadership of Red Hat. Okay, so we made it through 20, 35 minutes through that section. Now we'll talk about architecture. How are you all doing? It's tough? All right. It gets worse. I'm enjoying this part now. Okay, so Service Bus has a 3-tier architecture. This is the first time we're showing you kind of the inside of it. So what you're seeing from the outside is really just the gateway. You're seeing my namespace.servicebus.windows.net, the CNAME of our cluster IP address, and then behind that are just, you connect via AMQP or HTTP to a thing of what happens inside that thing. There's 3 layers. The first is the gateway. The gateway takes care of the connection management. It also does IP filtering, VNet management, and private endpoint support, which means all the networking features are happening there. It does terminate transport level security, but transport level security is used all the way also through the backend, but the external TLS termination is happening at the gateway. Quick anecdote of a funky a support case we had a while ago. We used to not have TLS enabled between the gateway and the backend. We used to do that on plain sockets because we're in a VNet, everything is safe, and all of a sudden we had errors that were show up, message corruption that was happening, and that's something that's not supposed to happen. Messages were landing in they were safe kind of in the tenant boundaries, but data just got weird. So we had some customers reporting issues. Turns out, make the story short, we had a router, a network router, that was corrupting packets, had a memory error. And that router was making what we found is that the checksum that's in TCP has only 1 byte, and the checksum was correct often enough on the corrupted packets that the socket would not break, but it would basically compensate with resends. And so that was undetected for a little while, and then we found out what that was, and the fix for us was put TLS on it, because TLS has better checksums and will catch that. So now we do TLS not only for the purpose of security, but also for integrity of the traffic, and that's the easiest way to go and achieve that. So be careful. It turns out that routers can cause really terrible things, and that's something that is a totally freak accident, but it happens to us because we do a lot of that. The backend is responsible for managing the log, but basically for putting the data into the storage system, and for sequencing, so labeling the sequence number, doing the timestamping, doing indexing of the messages, also for keeping track of the message life cycle. So all the things that I've told you as features, they're all happening in the broker. And then the storage layer is our log store. Effectively, that's how we go and store the data on disk, and we do this triple replicated across availability zones. What you buy in premium as messaging units is all the middle thing. The gateways is always shared, and the backend is what you buy as messaging units. So let's go and drill in further on that. One of the things that we do to make sure that your data is safe, but also that your broker is always available, is we split those brokers up into very many machines. Our broker sizes are typically 32, 64 VMs that are making up one broker. Those are, as I'll show you in a moment, then connected into a common cluster, and that cluster is spread across fault domains. A fault domain is there's a rack that's a fault domain. The rack has multiple VMs on it, and it has one power supply and one networking feed. That's one fault domain. It's actually not exactly precise because we also consider rows of racks as fault domains. And what we want to ensure is that in your broker, which is then running in the data center, that no two machines which own your stuff are sitting within that same fault domain. So they will never be sitting on the same rack. Then we have availability zones, and we have that available in most of the major regions in the world. And availability zones means there's a data center, a completely separate data center, separate networking, separate facility, typically separated out also physically, such that if a jumbo jet or parts of the ISS, whatever, right, crashes into the facility, the other two facilities will be unharmed. That's the principle. There's for each region, there's studies being done along the axis, I think 55 factors of what are the risk factors in that region: earthquakes, flooding, aircraft crashes, all those things. And based on that, they decide how wide the separation needs to be, but it's often in the order of 10 miles. Okay, so we take care with that cluster that one cluster is spread across those availability zones, so that if an availability zone dies, your cluster will still work. Your namespace will be unaffected by it, even though it's just completely losing part of that capacity. You don't see any of this. It's automatic. we just take care of that for you. This is how this works. The backend and gateway clusters are effectively a set of VMs that are being placed into the data center by Azure Virtual Machine scale sets. So we tell a VMSS that we need to have a cluster of whatever 64 machines. And VMSS is now responsible, per the policy we give it, to make sure that those machines are being placed across those availability zones and across those fault domains, such that if any one of those fault domains fails, if some individual machine fails, if a rack fails, if a networking device fails, if an entire data center gets destroyed, there's still enough capacity there, and that we maintain SLA while that happens, right? It is unacceptable when a data center gets destroyed, physically is on fire, that we drop SLA, right? Unacceptable. And we do drills like this. We basically just turn off the entire facility at once, cutting enough from networking. So there are also power outage drills and all those things. And we need to make sure that we stay within SLA. And then there are Service Fabric. Azure Service Fabric is the cluster manager that we use. And that is helping us in doing leader election. Who owns what means which queue is being placed where, because there needs to be that thing that does the sequence number, right? That's one authority. Which VM does that need to live on? And then also looks up the leader, because the gateway that wants to send messages to a queue that needs to route to the broker, that needs to go and find the broker that owns that queue. So that lookup is done also through Service Fabric. Service Fabric does the whole management of who owns what. And Service Fabric is also our hosting model, and that's where we activate the roles. So a process container is being held by Service Fabric, and Service Fabric is effectively, we're telling Service Fabric, you can only place one role on a given VM, either a backend or a front end. How you choose this is up to you, so this is completely automated. We don't influence that at all, right? And then the process container starts. The process container, we use container here as a model. Don't think Kubernetes, right? We actually run on Windows. And a process container is effectively a Windows abstraction here that is hosting then multiple processes in parallel. But it's something that runs on top of Azure Service Fabric. The principles for the backend is that everything is automated. There's no manual intervention we do. We don't do anything in terms of processing, placement, etc. And all the reshuffling is all done automatically. We have no influence on that. Every upgrade that we do is like a little outage, in that some machines come down, they get new bits, they get updated again, and we do this all within SLA. We do upgrades within, all the time for all kinds of reasons. The operating system gets upgraded, patches get applied, and all those things, and we maintain an availability rate of better than 4 nines while we do this. There are no service windows, there's no outages, there's nothing that we need to go and tell you about. It's automatic. And the thing will always be there, even through upgrades. That's why we don't do any warnings of upcoming upgrades. We can upgrade in everybody's production peak because of the way we do this distribution. The way how we allocate namespaces to those clusters is based on heuristics in terms of standard. We kind of have a notion of how much capacity will be required, or deterministic by buying effectively capacity via premium. The workload placement, so now we have the gateway and the backend. These are the roles that have now been chosen by Service Fabric effectively for those VMs. The workload placement is such that for the gateway, the workload placement, meaning the connection coming in, happens through the load balancer, right? The load balancer comes in, and then it says, here's a connection, and that connection is picking its host, if you will, through the load balancer. And so that's where the bucket of state is being established. That's where the authorization context lives. That is where anything is related to that particular connection or session or links is hosted. So that's how that work placement is. That's normal as you would have it in a normal web application. The entities, which, what is a queue, is managed by that gateway layer. That gateway layer is understanding what a queue is and what a topic is and what those things are. The backend layer here only knows logs. So that doesn't care about what that queue is named. It just has a logical name for a thing, and it goes and manages the thing. It manages the queue effectively. But the fact that it is a queue that belongs to namespace X and is something that is not known to the backend because the backend doesn't care. The Service Fabric placement here is done, the placement here is done by Service Fabric. What it does is it says, I need to activate a queue, and now it finds a machine with the appropriate machine in the cluster all by itself and says, and it's activating the queue over here. And that then maintains it maintains the queue there, sequence countering, and all the features that I talked to you about. And so when a request comes from the client to the gateway, it creates a connection, and then there's this routing that happens, which then goes and lands in the process container that then is managing that queue. Completely automatic. Now, also important for the placement is that every primary also gets a secondary. Service Bus Premium is special in that you get a dedicated broker process that's just yours. So when you buy one MU, you get a core that's yours, and you get memory that's yours. So the memory is exclusively reserved for a broker process, and then the more MUs you buy, the more cores we're giving you for this. So you get your own broker, but it's a broker that sits inside of this giant monster of cluster. And what's important is that not only do you get an active broker, but you also get reserves for that same capacity somewhere else in what we call a designated secondary. So when that broker process fails, when that broker process, which is currently owning your queues, when that is no longer there, then there's an automatic failover and basically instant new process that's being created on the alternate broker that's already designated, knows about this, and also gets basic copies of that volatile state all the time. So fire in a data center, that's currently where your broker is, right? That gets turned off within milliseconds of there being a failure that's being considered by the system as fatal. And then the failover happens automatically somewhere else in another data center. And the way how the networking works, et cetera, to find that new machine is also all automatic. Those failovers happen in seconds, and the clients that are communicating with the broker will typically cover that with their retry policy, so you won't notice. We have virtual networking, and we have firewalling built in. So it's not always a public IP address. In many scenarios, Service Bus is used inside of a VNet. So first, let's talk about the public networking. Public networking, as I said, you have a CNAME, Clemens v AMS.servicebus.windows.net that points then to the actual deployment name of your broker. And that's generally stable and will rarely change. There might be failover situations in which the address changes, but usually it's stable, right? And so you can go and depend on that IP address also for firewalling yourself. We have an IP filter that sits kind of in front of all the gateway machines, and those will go and then look at effectively the ambient IP addresses that are coming in, and will then go and deny or allow operations based on how you define the filter rule. So that gives you a proper firewall that you can go and control yourself as you like. There's also a mechanism for you to find out what those addresses are, but DNS rule, if you create a DNS rule, if you come from your own on premises, then you can create a DNS rule basically on this or on that, and your router, your firewall, your outbound firewall will know. We support WebSockets on AMQP, which means if you want to come through 443, you can. And that's something that is very commonly used, and the performance loss through using AMQP is also very minimal. It's like, you shouldn't think about it. For VNet, we have a feature called private endpoints and also VNetting. And generally how this works is we have an internal IPv6 address that we also associate with a cluster that cannot be seen from the outside. And then you're binding effectively your customer virtual network using that private endpoint mechanism to that IP address. You can't do that. That's something that we have to go and do. But what happens is that effectively this private endpoint address that sits inside of your own VNet gets pinned to this IP address so that our broker just shows up then in your VNet as at that address. And then you can go and give it also your own name. If you come from the outside, you must use this name, right? Otherwise, we can go and identify this on where this comes from. So this is all magic to make sure that you can have private traffic into your namespace. We isolate the traffic. We're still all running in multi-tenancy, right? But you have it isolated, which means there's premium. Your memory is isolated. Your processing is isolated. And then also up to the networking stack, your traffic is isolated from others, but it's still a multi-tenant model, which means you get the effects of us running that for very, very many customers at the same time, the reliability effects of that, while getting effectively full isolation of your data and of your traffic and your processing capacity. One of the wonderful things about the networking features, that ability to go and join one or multiple VNets, is that Service Bus can also serve as a bridge. You can have Service Bus activated on a public network and on multiple VNets. Those networks will not touch, but they all attach to Service Bus, which means that you can use Service Bus as a very safe bridge to move data between those isolated subnets, basically between your isolated environments, right? And then you are not exposing your safe zones to external traffic at the lower level. It's all layer 7 networking. And that's something that customers who are very concerned about security do often, is that they use effectively Service Bus as the way to get data in and out of a safe zone for their systems without having to create networking rules and NATs, etc., that are all more error prone than this would, because this is a very safe method to go and get that data across. Service Bus has two authorization models. One is for SaaS, shared access keys. If you want to have a model where you simply have a name and the key, you can go and do that. Or you can have the full AAD, Active Directory identity integration, which means you can use authorization against Service Bus without being integrated in AAD, right? Username and password in the simplest case, or you can use the full AAD model if you like, and then also authorize against them. The way that works is effectively you have in SaaS, you have a rule and a key that's associated with an entity that's down here or with a namespace, and then the client can either go and create effectively a token locally using the rule and the key, or it can also call a custom token service that can be effectively any web service, right? And that has the rule and the key, and then you go from the client to the custom token service and say, hey, I would like to have a token. The client needs to fulfill some requirements, and then it gets the token assigned by that custom token service, and then it can go and use that against Service Bus. So you can build your own authorization scheme if you like, using that model. Or you use effectively the Active Directory built-in model where you have an identity, then you effectively grant the service access in using the Active Directory model, and then we use the policy engine of Active Directory to check whether the token is actually valid or not. So two distinct authorization models, and you can also go and take that model and turn it off completely. That's a new thing we added in the last few months because some customers were complaining that there are two models. And so if you want to go and only have AAD, you can also have that today. And then lastly, let me talk about performance and reliability. Throughput. In standard, there's a soft throttle of about 500 messages per second per namespace. There's a credit-based model that's documented on the site. It will go faster. It will also go faster in bursts. You should not rely on that, though. We will throttle you when we see you over that limit. Service Bus Premium is really only limited by how much capacity you are allocating, and if you're hitting your CPU limit on your MUs, well, you're getting throttled because of that. The way how you can go and deal with that is you can go and upgrade the number of MUs, and you can go up to 16 MUs, 16 cores that are associated with your namespace, and that creates a pretty big cluster. Every single log can do about 10 megabytes a second of data I/O combined. 5,000 messages a second at 1 kilobytes per second if you do things right. You need to, if you optimize for throughput, you need to go and make sure that you have messages on the wire at all times, like you don't individually go and do a wait on every send. You use batching, etc., but then you can go and can get that throughput. Why is this 5,000 here? Well, because you need to go and send messages in, and you need to send messages out, and that's kind of the combined throughput you can get. More features, if you use more features, topic rules, SQL, all those things, that will obviously impact your throughput. CPU goes up, and that will impact the throughput. But you can get, we basically expose the metrics to you. The monthly global uptime, are the endpoints reachable, is 100%. Service bus clusters are always up. The reliability, which means what's the rate of trying and succeeding with an operation, is in excess of 99.995%. It's often hitting 5 nines and better during the course of the day. That count towards that error rate counts everything we do intentionally, right? If there's an upgrade, there will be an error that you get back sometimes, maybe. If your broker fails over, if we rebalance, all of that counts towards that rate. Our clients will go and automatically retry on anything that's transient, which means that typically your user experience is going to far exceed that rate that we observe on the server side by at least an order of magnitude. It's ultra reliable as a service. And that's why a lot of customers love it. So, leading reliability and availability, 0 downtime, no servicing windows, right, compatible with JMS2. And I hope this was an interesting tour through the internals of Service Bus, and that was the first time that we really shared that in that level of detail. And I hope that kind of helps you having confidence in the things that we're doing here for you in messaging. Thank you.